asking us to use these transformations, but put them in the correct order. So to x cubed, I have to do this first because it says reflect with respect to the y-axis. So when I do this, now I have to be careful. So this is the first step. So remember x cubed. We graphed x cubed some time ago when we talked about odd functions. So this is x cubed. Now the reflection with respect to the y-axis will make this. So this will be negative x to the third, in parentheses negative x and 3 outside, which will be negative x to the third. Now this purple graph has to be moved 2 to the right, but inside, right? So x cubed was number 1, and number 2 will be negative x cubed. Number 3 will be negative stays outside, and I have x moving 2 to the right. So this is x minus 2 to the third. So now this is done. This is done. Now vertically vertical shrinking by a factor of 1/2. Exactly, that is straightforward. So this is number 4, negative 1/2 x minus 2 to the third. So now this is done. And final step is up 1. So negative, yes, x minus 2 cubed and plus 1. And this is final. So it's a little bit tricky here. We will come back here in this section to this, come back to the handout. So that's all in chapter 2 that they want us to look at. Okay, so last time we talked about the concept of common domain. If you remember, we cannot add, subtract, multiply, and divide if those functions don't have a common domain. And furthermore, when we divide, the denominator cannot be 0. So let's look at one other situation with, I don't remember if we did 26 or 25. Roberta, can you look at which one was the last one?
We did 26 and 27.
Okay, then. I think I'm fine. So now let's look at, let's say, problem 34 on page 297. They're asking us to find all these functions and the domain for each. So I would like to write a note. Note, the sum, the difference, and the product will always be defined on the common domain. The ratio may or may not. So the sum, the difference, and the product will always be defined on the common domain, but the ratio may or may not. So in this case, we are given f of x, and that is in 34 x minus 6. And they're giving us g of x, and that is 5x squared. So they want us to find f plus g, f minus g, fg, and f over g of x. Before I attempt to write these functions, I will find the domain of f. Can anyone give us the domain of f and the domain of g? What is the domain of f and what is the domain of g? Is there a ratio? Is there a square root? No. So what is the domain of a polynomial function, no matter what polynomial function I look at? All real numbers. There are polynomial functions, no restrictions, friendly functions, defined everywhere. So then what would be the common domain? Right, negative infinity to infinity. So now I can go ahead and write, I have to write the definition as f of x plus g of x, and then just put them in. X minus 6 plus 5x squared, and this is it. I created a new function by adding two other functions. Same thing with f minus g. I write f of x minus g of x. I write x minus 6 minus 5x squared. It's more writing than thinking in this section. So now this is f of x times g of x by definition. So I write 5x squared times x minus 6. And I'm done. You could distribute if you wanted to into 5x cubed minus 30x squared. But now when I write the ratio, f over g, this is f of x over g of x, I copy x minus 6 and I copy 5x squared, and I have to put a comma and I have to write if. Excellent. So as you see, in this particular case, the first three functions were defined on all real numbers, but can anyone give us the domain of the ratio? Very good. Now, let's talk about, before we choose other problems, let's talk about the fifth way of determining new functions. So we know that we have four ways. Can anyone repeat those four ways of finding new functions from given two functions? I'm given two functions, what, in how many ways I can... Right. So there is a fifth one. Fifth one is function composition. This is none of the above ones. None. It's not addition, it's not subtraction, it's not multiplication, it's not division, it has nothing to do with those. The notation is F, a circle, and G. Or G, a circle, and F. Of course, this is not the way we read it, but F, comp, G, of course, of X. And this one will be G, comp, F. In other words, the composition of F and G or the composition of G and F. Are they different? Yes. Will they ever be the same? Yes. In a very specific situation, which occupies the entire section 2.7. Okay. So let's say I have the same functions. I'm given f of x, which is x minus 6, and I'm given g of x, which is 5x squared, assuming I use the same functions. Now let's look at three bubbles. This is x, and I apply function g to it. What will I get? Right, I will get g of x. So when to a number I apply a function g, I will get g of that number. But this is a number as well. So now let's say to this number, so this is 5, I apply function g and I get 10. And now to 10 I apply function f. What will I get? I get f applied to g. So this is f of g of x. The first function that was applied is the one the closest to x. The second one is what it's called the outer function. So this is the inner function. Why? I apply it first. This is the outer. Why? Because I applied second. If we go back to what we just looked at a few minutes ago, in this function, which is the inner function, the very first step that I have to perform, that is the inner function. Of course, what is the outer function? There is more than one. No, not yet. The outer function is f. The inner function is this, the outer function is f, and the even further outer is 2 times f. Right. Good. So since we apply G first and F second, this is what we call F comp G. So it's F of G of X. Now I have the other way. Here's X, and let's say I apply F to it. What will I get? Perfect. And now to this number, because it's a number eventually, I apply G. What will I get? G, right, G of F, or in other words, G of F of X. So now G comp F of X is G outside, and F is the inner function. And we're going to do the exact same thing, what you see here with these two functions. So please dictate when I want to find F comp G. I must write the definition of F comp G is F of G of X. And I have to replace the inner function by, so this, don't erase it like that, I'm just making a point. What is that? What is G?
5x.
Very good. So now I'm asked to find F of something, but by definition, F of something is something minus 6. So how will you write the final answer? 5x squared minus 6. Something minus 6. Now if I want to determine the other way around, the G comp F, I have to write the definition first, which is G of F of X, and I have to replace I have to replace F by what it equals to. What does it equal to? Very good. But now I look at G. G says G of whatever is 5 times whatever squared. So what will you tell me to write? You need to tell me 5 times whatever squared. Squared. But now I have to square, and we have a contract on this. I hope you're not foiling still. I hope we are done with foiling. So this is 5 times x squared. 2 times the first times the second. Very good. And plus?
36.
Very good. And yes, I will distribute and get 5x squared minus 60x plus, what is this? 190? 150 plus 30, 180. This is the way we create new functions. I didn't mention anything about domain. Here's the problem with these two. Potential problem. Potential problem. So I apply G to X. This is the domain of G. So I find the domain of G and I apply G to X. And I get a number. What does this represent for G? If this is its domain, what is this? Of course. So this is the range of G. However, this identical set must be the domain of F. So this is also the domain of F. But what happens, and if I bring with G negative 5, but I cannot apply F to negative 5. The chain will not continue. The chain will be broken. So I apply to 5 G and I get 10. But then F cannot be applied to 10. So I cannot get to this set because F is not defined at 10. So this concept is dealt with in pre-calculus and calculus more than here, and I'm not going to make a big fuss out of it because the book chooses examples in which the range of F and the range of G and the domain of F match, because otherwise we will never get here. So I will leave that alone. So just keep in mind, this is not about common domain. When we talk about function composition, I'm going to write this down. Note, function composition does not require common domain. Do not ever talk about common domain when it comes to function composition. It means nothing. However, I'm going to say, if the range of the first function, I should say maybe inner, does not work well, and you know what I mean, with what? With, so function composition does not require common domain. However, if the range of the inner function does not, quote unquote, work well with the domain of the outer function, comma, the chain will be yes. So this is the danger. The danger is that the range of the inner function may not work well with the domain of the second function, and you will not be able to continue. It will be broken in the middle. So one more time, function composition does not require common domain. However, if the range of the inner function does not work well, and you know what I mean by work well, with the domain of the outer function, the chain will be broken. In other words, f come g or g come f does not exist. Okay? I would like to look at few problems from 75 through 82. (75 through 82) on page 298. All functions are function compositions, all of them. And they want us to break it up. So, for example, problem 79 has h of x equals the absolute value of 2x minus 5. They want us to identify the inner function and the outer function. And I want to caution you that there is more than one correct answer here. So they want us to find two functions, the inner, which I would like to denote by g, it doesn't matter really, and the outer. So look at this function and say, I know the inner is this, the outer is this. And if you create a f come g, you will get h. Inner function. In other words, what will you evaluate first? What will you apply if I ask you, evaluate this function for x equals 0? Where is your starting point? Which function will you apply to 0 first?
This one.
Say it again.
Minus 5.
No. Which is? I ask you evaluate h for 0. What will you do? In what function? Exactly. Right. That's your inner function. You're done, you get a number. What function you apply now to that number? One number. Which function? Which function would you apply to the result? So I'm asking you to evaluate this for a number. You get a number. Let's say you get 15. What function do you apply to 15 now?
The absolute value.
Correct. So the inner function is 2x minus 5. The outer function will be the absolute value of x. When you create the f come g, you will get h of x. Is that clear? Okay. Here's another, like 81. They want us to decompose 81 into an inner and an outer. So please give me the inner. Say it again. I could not do that first. 2x minus 3. Once I'm done with 2x minus 3 and I get 15, what function, let's say, I apply to 15? That will be the outer. 1 divided by x. That is the function we apply to the result. Any questions on this? Are we okay with this? Please say no if it's not clear. Yes. Let's say 77. We are given h of x, which is the cube root of x squared minus 9. We can decompose these functions sometimes, or more than sometimes, often, into more than 2 functions. But this time we are only asked to find an inner and an outer. And again, there is more than one correct answer. What will be the inner function that you will evaluate first?
X squared minus 9.
Excellent. You're done, you get 15. What function will you apply to 15? The cube root of x. If you would try to create the composition f cum g, this is f of g of x. Let's say we want to check, which is f of x squared minus 9. And I look at f. F says f of whatever is the cube root of whatever. So what would you ask me to write? The cube root of? Is this better now? Perfect. Now I would like to look at some graphs. I would like to look at 85 and 91. And this was my 4, 5, 6. Okay, 85, we are asked to find fg of 2. We are not given the function, we are given the graphs. So first of all, what will be the definition of this? Before I even look at the graph. What does this mean, really? F, it's not f of, it's, yes, f of 2 times g of 2. So now let's look at the graph and identify f of 2. F is in blue and g is in purple. Can anyone give us f of 2? F of 2, f is in blue.
1. No. Negative 1.
Do you agree with negative 1? You agree with negative 1? Okay. Now, can anyone give us g of 2? G is in purple. G of 2 is? Do you all agree with g of 2 being 1? Yes? Okay. So then the answer is of f g of 2. Yes? John, you had a question? Okay. So negative 1 times 1 is negative 1. Let's look at 91 now. At the bottom graph. F cum g of negative 1. First, the definition. What do I have to write before I even look at any graph? I have to write f of g of negative 1. So now I have to identify this. So let's look at the second graph, the bottom graph. G is in purple. I need to find g of negative 1. G of negative 1 is? The bottom graph, G is in purple.
Negative 3.
Negative 3. So this is negative 3. So therefore, what am I asked to find? What do I continue? What do I write?
F of negative 3.
Excellent. F of negative 3. Let's look at the purple. I'm sorry, the blue graph, and determine f of negative 3. 1. Do you all agree with 1? Good. Do you think we need another example from each? Please choose. I'm more than happy. Let's say 86. So G over F of 3. First, what does this mean? The definition. This is
G of 3.
G of 3, excellent, over
F of 3.
excellent. So let's go. This is the top graph. G is in purple. G of 3, please.
Negative 3.
G of 3. G is in purple. One more time. It's exactly where it crosses the x-axis. That's 3. So it's 0. I still have to find f of 3. So let's determine f of 3 with a blue.
1.
Negative 3. How much is 0 over negative 3?
0.
0. Okay, let's do 94. Any questions? Stop me, please. G comp f of negative 1. I have to write the definition before I look at the graph. What is the definition of what we are asked to find? G of
Negative 1.
excellent. I have to start with the inner function. First, I have to find f of negative 1. F is in blue, so f of negative 1 is? Do you all agree? So therefore, what am I asked to find? I'm asked to find of? Very good. And now I go to the purple graph, and G of 1 is? Negative 5. For those of you who have a book, would you like to share with your colleagues so they can look at this too? Okay? Okay. Now, 2.7 inverse functions. Let's talk about the following scenario. Can we think of two functions that if I apply them in any sequence, so let's say function f and function g, I apply g to x, and then immediately I apply f, and these two functions cancel their effect on x. Here's an example. If I multiply x by 2, but then immediately I divide the answer by 2, what happened to x? Nothing. Right? The second function cancels the effect of the first one on x. And I can do it the other way around. So I can divide x by 2, but then if I multiply the answer by 2, the inner and the outer, if the inner function is multiplication by 2, but the outer function comes in and divides the answer by 2, what happened to x? So this is a very specific case, and it's called, well, one is called the inverse of the other, because it undoes the effect of the first one, right? It's the effect of one is undone by the effect of the other. Yes, please.
Can you do x squared and x squared?
Yes, but there are some problems with that. Very good question. There are some problems with that, because, and I'm going to talk about which functions have inverses. Very good point. So can anyone give us another example in which one function, the effect of one function is like, for example, I'm giving you $10 and then I'm taking it back. So giving you 10 is one operation that was undone by taking it back. What happened? What was the deal? Nothing. Nothing happened. You didn't gain anything. I didn't lose anything, right? So nothing happened to x. So can anyone give me an example of two functions that will applied in any sequence, function 1 and then function 2, or function 2 and then function 1? Nothing will happen. At the end of the day, nothing will happen to x. Two functions. There is a little problem with x squared, so I don't want to talk about that just a second. I want another example, not with x squared, but you're right. But there are certain conditions have to be fulfilled, and I'll explain them in a minute. Okay, exactly what I just said. X plus 10. And what will be the operation that will undo the x plus 10? Right. What do you think will happen We already discussed that. When I determine f come g, or I determine g come f, what will the answer be?
0.
Cannot be, because I have x. So I have x in my hand. I'm giving it to you, and I'll take it back. But I still have my x. So I'm giving you 10, and I'll take it back. But I still have my x. What happened to x? Nothing. So this is the answer. And this happens only if f and g are inverses of each other. So this is the property of inverse functions. Property of inverse functions. Let's check with the two functions you gave me. So let's find f come g. F of g of x, by definition, which is f of x minus 10. I have to plug in x minus 10 in f. What does f say? F says blah plus 10. Whatever plus 10. So what will you tell me to write?
X plus 10.
This is the blah. So I have to write x minus 10 plus 10. So what is the answer? Right. Not 5x, not x squared, not x over 3. Plain x. Nothing happened to x if I give you 10 and I take it back. What about the other one? What about g comp f of x? Which by definition is g of f of x, which is g of x plus 10, because that's what f is. And now look at g. G says g applied to blah is blah minus 10. What should I write? Which is? So it's guaranteed that these two functions are inverses of each other. One cancels the effect of the other, applied in any sequence. So before I explain when this happens, I would like to look on page 309. And let's say we look at problem 5. And I have f of x equals 5x minus 9, and g of x, which is x plus 5 over 9. I'm asked to show whether f and g are inverses of each other. I don't know. Besides, even if I knew, they asked me to prove. So what will prove that these two functions are or are not inverses of each other? What do I have to do with them? What do I have to find, determine, calculate in order to show yeah, or say yeah, they are, or no, they're not? I have to find f come g, and I have to find g come f. Only if both are
X.
exactly x. Exactly x. Not x squared, not x over 3, not 5x. So if I determine the function composition, f come g, and I determine g come f, and both of them give me plain x, what do I conclude about f and g? Because this cannot happen unless f and g are inverses of each other. And you can say, okay, what's the big deal with this inverse? In a moment, I'll explain why this is such a big deal. Okay, so I have to find f come g. By definition, this is f of g of x, which is f of x plus 5 over 9. Now I look at f. F says 5 times blah minus 9. How do I write that? 5 times 5 times,
X plus 5
yes?
minus 9.
So I'm just checking to make sure it was 5x minus 9 and x plus 5 over 9. Okay, very good. So f of this is 5 times this minus 9. Okay. Whatever I do, it's 5x plus 25. I multiply this by 9 minus 81 divided by 9. I get 5x minus what is this, 56 divided by 9. Does this equal x? What do I conclude? I don't have to find the other one. I don't care what even the other one could be. It's not. Not inverses. They're not inverses of each other. Very good. Okay, let's look at one more, like number 3, where I have f of x equals 3x plus 8, and g of x, which is x minus 8 over 3. Same question. I'm asked to show whether these two are inverses of each other. What do I have to determine? I have to find the function composition f comma g, and that will be f of g of x by definition, which is f of x minus 8 over 3. Now I look at f, and f says 3 times blah minus plus 8. How do I write that? Times
X plus 8
x minus 8 over 3
plus 8.
plus 8. So what should I do first? I won't, because it's easier to simplify. Because if I distribute, then I have to divide after that. So what is left? X minus 8 plus 8, and the answer is x. I will ask you to do this on your own. What do you think the answer would be? But please do it for practice. This is very important. What do you think the answer would be? But we have to show both. X. Then what do you conclude about this f and this particular g? They are inverses of each other. This will not happen unless these two are inverses of each other. Okay? Therefore, inverses of each other. What? Yes.
So during the test, you have to show both.
Yes. So now notation. Here's the notation for the inverse function. And this is the way we read it. F inverse of x. This is not f raised to negative 1, and it does not mean 1 over f. This is a simple notation that says f inverse of x is the function that is the inverse function of function f. That's all it says. Now, super important, not all functions have inverse. This is very important, function. What does that mean? Can I find an inverse for almost everything? Yes. But not all of them are functions. So we are interested in functions who have a specific property whose inverse functions are also functions. Can all functions have an inverse? Yeah. But not an inverse function. Not all of them have an inverse function. So the inverse is not a function always. So, which functions have inverse functions? So that's the property. Only 1-to-1. 1-to-1 functions have inverse functions. And now, of course, the question is, what is this? 1-to-1. Okay, here's the explanation of 1-to-1. And why only 1-to-1 functions have inverse functions. Some time ago, we talked about the definition of a function, and we said this. And then we said this. Is this a function? Each x corresponds to only one y. Is this a function? Each x corresponds to only one y. One more time. Is this a function?
Yes.
It is a function. Each x corresponds to only one y, right?
Yes.
Good. Now look at this. Going this way, is this a function?
Yes.
This is 1 to 1. That's why it has an inverse function. Now let's go backwards. Is this a function? No. So not this function f, not 1 to 1. Therefore, it does not have a function. It doesn't have an inverse that is a function. So this is the property of 1 to 1. Not just one x corresponding to only one y, but also one y, or each y corresponding back to only one x. So this is the property of 1 to 1. In other words, 1x, 1y, 1y, 1x. Yes, please.
That's when you set those conditions in.
Yes, because x squared is not 1 to 1. For this particular y value, I read two different values of x. So here are several functions. Do these represent graphs of functions? By the vertical line test, all these are functions. Would you agree? Which means each x to only one y. But what about crossing those functions with horizontal lines? For one y, I get only one x. For another y, only one x. For this y, only one x. For this y, only one x. This is 1 to 1. It will have an inverse function because it's 1 to 1. What about this one?
No.
Because for this y value, I read 1, 2, 3 different x values, which means this is this. I have 3 x values that go to the same y value. 1, 2, 3 x values. 1, 2, 3 go to the same y value. So it's a function, but not 1 to 1. Therefore, it will not have an inverse function. What about the quadratic function? Not 1 to 1. We can always make 1 to 1 functions from functions which are not 1 to 1. What if I say to you that this function, for some reason, is not defined on all real numbers, but it's only defined between 0 and infinity? Does this become now a 1 to 1 function? Yes. So with certain restrictions, I can, although it's not 1 to 1 because of this, I can make 1 to 1 functions from functions that are not 1 to 1. And I have only 8 minutes left. I just want to, it's not done, obviously. I didn't finish this, but I just want to show you the procedure of finding the inverse function. So can you tell me whether, let's say, 3x minus 4 is 1 to 1? Think of its graph, think of what it is, and let's just write a note. This function is 1 to 1 because blah. All of the functions that I showed you are continuous. What type of function is this? Linear. So for every y value, it will cross because it's linear. So it's linear. Linear function. Therefore, it is 1 to 1. You can write in parentheses by the horizontal line test. So now the requirement is find its F inverse. So I know it has F inverse. Therefore, I will write therefore F has F inverse because it's 1 to 1. And this is a 4-step procedure. 1, 2, 3, 4. Like similarly with completing the square. In step 1, I replace f of x by, what can I ever replace f of x by? Exactly. So then I have y equals 3x minus 4. In step 2, I swap x with y. And you can say, wait a minute. So here's x. You're getting to y. So this is your f. But now you want this to be f inverse. So now I'm replacing y by x. Why am I replacing y by x? Because the inverse function will be defined here. Will be defined on this value, which becomes its x. So that's why y from f becomes x for f inverse. That's the only reason why I'm allowed to swap. So now I say x equals 3y minus 4. In step 3, I solve for y. Why? Because y will be the new f inverse. So can you tell me how to solve for y? Add 4 and divide by 3. So then y equals x plus 4 divided by 3. In the final step, replace y with, or by the notation, what? F inverse. So f inverse of x is x plus 4 over 3. I will denote this set by A, and I will denote this set by B. Can anyone clarify? And this is the mathematical way of writing this. You don't have to write it like that. It's just easy, I think. F is defined on which set? A. And it takes values, or its range is? Can anyone give us the same thing for F inverse? Its range and domain. Domain is very good, and its range is exactly. So that's the reason why the y value for f becomes x value for f inverse. And that's the property of the inverse function. It takes things back where they came from. So 5 goes to 10, and 10 goes back to 5 with the inverse. Okay, I have 3 minutes left. So now I found that f of x, which is 3x minus 4, has an inverse function which is x plus 4 divided by 3. Now the final step, I would like to graph f and f inverse on the same coordinate system. That's the last thing I want and I can't do today. Bless you. So let's find the two ordered pairs. It's a linear function. When x is 0, y is very good. So the ordered pair is 0, negative 4. And when y is 0, I move 4 and I divide by 3. So then x equals 4/3. So 4/3 comma 0. So I found the x and y intercepts for function f. It's a line. I'm going to graph it. So 0, negative 4. And 4/3, which is a little bit more than 1 right here, and 0. So I graph this line. And this is f of x, 3x minus 4. We just discussed this idea I refuse to calculate anything or determine points, but I would like you to tell me which points I should graph for F inverse.
-4.
Right, exactly. All you have to do is swap the two. Very good. -4 is 0. And
0.
very good. What do you notice? And before you say anything, here's what I'm going to do. Bless you. With respect to this line, and we all know what this line is. So this piece is reflected here with respect to this line. This piece is reflected here with respect to the same line. I need to identify that line. Thank you very much. So that's the final note for today. Note: the graphs of F and F-inverse are symmetric with respect to the line y equals x that bisects the first and the third quadrant,